Hi everybody, so I'm going to introduce the concept of calorimetry. Calorimetry is really just a measure of energy flow. We're going to look at two specific ways energy flow goes towards generally changing the temperature or internal energy of a system. We're going to do work in or out or heat flow. So this is important for a number of problems, especially the specific heat lab that we will do, or if we've already gotten the data, how to go ahead and solve for specific heat. Okay, so let's just jump right into it. So we have internal energy U, and it can be changed two different ways. You can have the traditional heat flow in or out, right? That's Q. Or you can do work on a system. There's W. Okay, so I will demonstrate in class, if I haven't already done so, a way we can show how work done on something can change the internal energy by raising the temperature. But in general, when you raise the internal energy, it goes towards a change in temperature. The only exception to that is when we have a phase change, which we'll discuss in a later tutorial. So the equation is some constant C times a delta T, and where C refers to heat capacity. We're not going to use this term too much, but in the IB, it's something you have to be aware of. So let me be clear if it isn't here. This should be a capital C, because we're going to see in a minute that there's a lowercase c that's similar, but not quite the same thing. So a very simple problem we can look at is, let's say I've got a hammer, or a hammer head that's being swung, and it is moving 5 meters per second, strikes a nail and comes to a stop. Okay, so all that kinetic energy, when it hits the nail head, goes, let's say, into the nail. And so it's going to go in the form of thermal energy or internal energy, and we can ask what's the change in temperature of the nail. So the idea is the change in temperature, C delta T, is equal to the internal energy change, and the internal energy change is due to the loss in kinetic energy of the nail. So if we solve for delta T, which is what we're interested in, then we can just say it's 1/2 mv squared. And it really should be v squared minus v naught squared, but one of them 0, so we'll just ignore that, divided by capital C. Okay, so this becomes 1/2 of 5, which is, 1/2 of 1.5, which is 0.75 times 5 squared, there's our velocity, divided by 4.5, and we're going to see 25 times 0.75 divided by 4.5. It's going to be a small temperature change. Actually, it's not as small as I thought. I've got a 4-degree change. I think I did that correctly. So that's 4 degrees Celsius, because our heat capacity is joules per degree Celsius. So you get a significant change, and if you ever pounded something and you feel the hammerhead or the nail after, you can definitely tell there's a temperature change there. Okay, now what is heat capacity? What does it depend on? Okay, so it depends on first the mass of the material. In other words, the more mass you have, the more heat capacity, as the name implies. So if you have a cup of water, it has a certain heat capacity. If you have a tub of water, it can hold more heat. Even that's really a poor way of putting it. It really holds more internal energy. And if you have an ocean, it has unbelievable amount of energy, as we will see on a homework problem sometime. But what also matters is the type of material. And that's what we're going to focus on, and we're going to revise this equation. So when you look at the type of material, you can talk about a property called specific to the material. Specific, am I spelling this wrong? Specific heat capacity. And I'm going to put the word capacity in parentheses because generally we just call it specific heat. And the definition is the amount of energy needed to raise 1 kilogram of material 1 degree Celsius, or 1 degree Kelvin, because changes in Celsius and changes in Kelvin go hand in hand, as we saw earlier. Whereas heat capacity is the amount of energy needed to raise a material 1 degree Celsius, okay? And that depends on both the mass and the material. So, for example, specific heats, water, so specific heat is given a lowercase c designation. And for water, it's actually a very high value. It's roughly 4,180 joules per kilogram per degree Celsius. where again, specific heat or heat capacity would just be, we saw before, it builds into it, or it doesn't have the mass in there. And whereas aluminum, which is going to come up in some of our examples, is significantly less, all right, 900 joules per kilogram per degree Celsius. Okay, and in the lab where you're doing for different metals, you see aluminum is the highest of the metals we sampled. And you'll need that value for the lab. So when we put it all together, the idea is if we do work on a system and it goes towards some internal energy, or we could just as well have a Q flow, okay, so I might as well expand that, then the equation we used before becomes MC. There's our heat capacity, delta T. So let me make that formal here, where heat capacity, capital C, is equal to M times little c. But we usually use this form, the MCAT, and you may remember that from chemistry. Okay, so let's do a problem. A waterfall has a flow rate of 200,000 kilograms per second, and it falls a certain distance. The water hits a 1,500 kilogram marble basin below and comes to a stop. What will be the temperature of the basin 30 seconds of falling? Okay, so we've got this waterfall rushing down, 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 and hitting something right there, and all that energy, okay, that's coming from a change in potential energy is going to warm up the basin. Now technically the water would warm up as well, but we're just going to keep the problem fairly simple. Okay, so what the idea is our MCAT, right, we're going to look at that, is equal to a change in internal energy. And internal energy in this case is coming from a change in potential energy. So it's delta UG. Okay, and so delta UG is mgh, and this is the water, so I'm going to put a W there where the mass here is the marble. And we didn't give the mass of the water, we gave a mass flow rate. So the mass flow rate multiplied by the time that we're interested in determines the amount of water times GH. So there is our input, here is our output. So if we want to solve for delta T, then we see it's m dot T GH all over M. This is the marble now, not the mass of the water. So these two terms don't cancel out, times the specific heat. Okay, I will let you work that out. Okay, I don't remember the answer off the top of my head, but I want to keep things moving. So you can check it out and then check with me in class, and I'll have solved it by then. Okay, I'm not going to have time to go over this now. If I have time in class, I'll show you where basically we can use electrical input. In other words, I've got a certain mass of water, we've got the specific heat of water starting at a certain temperature. I've got a power input from a heating element, so I put a little coil in that water at a certain power, and that would equal to a voltage times a current. We let it run for a certain time, and we can predict what the final temperature is going to be. And it's a good problem for you to solve. It's basically, right, power times time, which is the amount of energy, is equal to MC delta T. And what if we do it, we would get a prediction, and our prediction shouldn't be awful, but it's not necessarily going to be as accurate as we might like. And so when you're talking about experiments, especially in the IB, they want you to understand what are sources of error, right? So again, I have this element in some water, I put it in there, I run it for timing, and what are sources of error? Of course there's instruments, right? But we shouldn't expect that to be too bad. But you know what, if I'm going to talk about instrument more than anything, the thermometer is what I'm worried about most. I'm pretty sure I can time, especially if I run it for a few minutes. If I'm off by a half a second, that's not a big deal. Perhaps the most important, okay, even the less obvious, is you got Q from the environment. In other words, you will have energy loss to the environment because you are changing temperature. So let's say our water starts at room temperature. As we warm it up, because it's warmer than the environment, there's going to want to be heat flow out of my system. So I want to have a well-insulated system, but it's hard to keep that exactly perfect or perfectly insulated. So this is always a issue. You could have mass loss. In other words, if we're dealing with water, okay, some of it could spill out. And that's, especially with the specific heat lab, something we want to consider. Okay, and even we could have, and mass loss could also come from vaporization, right? Especially if you get really warm water, it's going to vaporize, and you're going to lose a little bit to steam. Not a big thing, but it can carry away also a decent amount of your energy. Okay, so let's move on. So the other way we can do calorimetry, and this is what the lab is going to be really centered on, is when you have heat conduction with two different objects of two different temperatures in contact. So schematically, I have a cold side and I have a hot side, right? They come in contact. This could be putting a hot object in water, where the water is, let's say, cooler than a hot object, and you're going to get heat flow from hot to cold. Okay? And the underlying law to help us understand that ultimately the equilibrium temperature or temperature change, whatever we're interested in, is that the Q into one is equal to the Q out of the other. So it's just conservation of energy. So I have, in the left arrow, we have Q out here, and we have Q in here, right, from hot to cold. And so how do we quantify that? Well, we have in the Q inside, we have, let's just call it M1C1, so that's the mass of the colder body, its specific heat, multiplied by whatever change in temperature it has. So I'm going to put a C there for cold, and I'm going to have M2 C2 delta T on the hot side. Okay, and I just set them equal to each other. Now this is going to be a really a pain to solve because the delta T's have pluses and minuses in them, or actually minuses. So in a really important aspect to make the math work out is on both sides of the equation, you must always make delta T positive, okay, which determines the order of what you put final and initial. So let's see if this makes sense. So if we're on the cooling side, which is this side, we want delta T to be the initial temperature minus the equilibrium temperature. Because if it's going to cool, that means that the initial temperature is going to be warmer than what we're going to finish at. So in order to make it positive, it's Ti minus Teq. If you're on the warming end of things, that means your things are going to cool down. So you're going to take your Teq is going to be bigger than the initial. Sorry, you're warming up. So your equilibrium temperature is going to be bigger than the initial. So in order to make that positive, that's how we set it up. So let's say I take 120 grams of aluminum at a warm temperature. I place it in 70 grams of water at room temperature. And room temperature, 20 degrees Celsius. What is the equilibrium temperature? So I'm just going to have time to set this up, and then I'll allow you to solve it. And it's not difficult to set up. It's just a bit of a pain. So what we have is, I'm going to, instead of using 1 and 2, I'm going to use, so I'm going to say mass of the aluminum, C of the aluminum, times delta T of the aluminum equals mass of the water, C of the water, delta T of the water. Okay, and I have to establish what is warming up. So the aluminum is going to cool, and the water is going to warm. So I want to make sure I have the positives in the right place there. Okay, so I'm going to factor out the MC for the aluminum. So I'm going to go MAl, CAl. And then for the delta T, I'm going to put the equilibrium temperature, that's what I'm solving for, minus the initial temperature. Okay, because the aluminum is going to cool down. I'm sorry, I've got that backwards. Yeah. So the aluminum is going to cool down, so I want the initial minus the equilibrium. And then I'm going to have the mass of the water, C of the water, and then I'm going to expand this to the equilibrium minus the initial temperature because the water side is going to warm up. Now let's anticipate what's going to happen. I have more aluminum than I have water. So we might anticipate the equilibrium temperature. We don't expect it necessarily to be halfway between 40 and 20 because we have more aluminum than water, but also water has a much higher specific heat. So that could offset it if we look at it. All right, so I want you to try to plug in the numbers. The specific heats are in the front of the notes. You're given the masses, and so work it out, and you should get an equilibrium temperature of about 25.4 degrees Celsius. So we are closer to the water than we are to the aluminum. Even though we have more aluminum, well, that's because the specific heat of water is about 4 times greater than the aluminum. Okay, and to finish up, you can try this one. Does a thermometer significantly affect whatever it's measuring? The answer is it can if you don't have a whole lot. So basically you're just going to do an MC delta T equals an MC delta T. Make sure you establish which is positive or negative, and if you solve it, you should get 40.8 degrees. So it has a small effect.